Hello and welcome to my presentation on OBD on UDS on CAN aka J1979-2. With my first slide, I'd like to tell you something about me. So who is Peter Subke? I am Manager Business Development, North America at Softing Automotive Electronics in Germany. I hold an academic degree in electrical engineering from the Technical University of Dortmund in Germany, and I'm involved in CAN-based hard and software for over 35 years, meaning since 1986 I grew up with a CAN bus. I published numerous technical papers, and I am the author of Diagnostic Communication with Road Vehicles and Non-Road Mobile Machinery, which is an SAE deep dive fact book available at the SAE bookstore or at Amazon. I am member of several SAE committees and task forces, and I restore and ride vintage Harley-Davidson motorcycles. As this presentation deals with OBD on UDS on CAN, I first should explain what OBD is. For the purpose of protecting the environment and thus human health, legislators such as the US California Air Resources Board or the European Commission mandate the installation of emission control systems on road vehicles, motorcycles and mobile machines. By 1996, the California Air Resources Board issued requirements for onboard diagnostics, OBD, today known as OBD II, a technology to detect and report emission-related malfunctions. Type approval is granted only if the emission of toxic pollutants does not exceed specific limits. Vehicles that are equipped with OBD systems must have a malfunction indicator light, a MIL, to notify the driver if there is a problem with the emission control system of the vehicle. OBD regulations require road vehicle manufacturers to install a diagnostic link connector, commonly known as the OBD II port, to connect external test equipment, in this context known as OBD scan tool. The photo on the left shows one of my vintage Harley-Davidson motorcycles. This is actually an FLH shovelhead, model year 1976, but 99% self-made. That is why I know that the electrical system of a vintage Harley-Davidson motorcycle is based on smoke. In production, smoke is pumped into the copper wires. If an electrical failure occurs, for example a short circuit, and the smoke comes out, you know that you are in trouble and you know where to look at. Today, the smoke-based diagnostics has been replaced by scan tool-based diagnostics. This figure shows the most important components of a diagnostic system. A vehicle communication interface, VCI, in the middle connects the diagnostic tester on the left-hand side with the diagnostic link connector, DLC, of the vehicle. The DLC is standardized in SAE J1962 and mandated worldwide for each and every passenger car. For the purpose of diagnostics, the scan tool sends a diagnostic service request to the vehicle and receives a diagnostic service response from the vehicle. Requests and responses are specified in diagnostic communication protocols. For example, the SAE J1979, also known as OBD II, or ISO 14229-3, which is UDS on CAN, Unified Diagnostic Services on CAN, or the new SAE J1979-2, which is OBD on UDS and serves as a successor of SAE J1979. Actually, the service tester does not talk to the vehicle. It is connected to the OBD connector of the vehicle, but the vehicle itself is not able to do diagnostic communication. It is the EE system that is connected to the OBD connector. And the EE system consists of control units, ECUs, such as the engine control module, ECM, or the transmission control module, TCM, and gateways, but also of sensors, actuators, bus systems, wiring, and connectors. So tester sends a request to the EE system and gets a response from the EE system. But to be honest, the tester does not talk to the EE system. For example, the wiring or connectors, but also actuators and sensors are not able to answer diagnostic service requests. Independent of the complexity of the EE system, at a certain point in time, diagnostic communication takes place between the scan tool and one selected control unit. So the tester sends a request to the control unit and the control unit sends the response back to the tester. Diagnostic service requests and responses are specified in diagnostic communication protocols. The current situation is there are 4 competing standards. One is SAE J1979, worldwide known as OBD II, in future named OBD Classic. There is also the European onboard diagnostics ISO 15031, which is pretty much the same as J1979. There is J1979-2, heavy duty OBD, and there is the worldwide harmonized OBD ISO 27145. So we have 4 competing standards. That's ridiculous. I think we need to develop one universal standard that covers everyone's use cases. Yeah, let's go for it. As a result, SAE J1979-2 has been published in April 2021. So we have 5 instead of 4 competing standards. And actually there is another one, the SAE J1979-3 is made for ZEV, zero emission vehicles on UDS. This slide shows the 9 OBD II classic services and the associated request service identifier SID between hexadecimal 1 and hexadecimal A. There is, for example, request current powertrain diagnostic data or request vehicle information, service number 9. If the tester sends a service number 9 to the control unit will answer with a negative response. I don't know what you're talking about. The reason is that the tester has to specify the specific vehicle information he is asking for. For example, the VIN, vehicle identification number. If the tester sends the 09 with a specific data identifier or info type identifier, then the control unit will answer with a positive response and the VIN if it knows the VIN. This slide shows the 26 unified diagnostic services as they are specified in ISO 14229. They also come with unique request service identifiers, for example the hexadecimal 11 ECU reset, but also the 19 read DTC information, the 22 read data by identifier, and the 31 routine control. Especially the 14, the 19, the 22 and the 31 are reused to specify diagnostic service requests for OBD purposes. Services that are marked with little dots are parameterized by a subfunction byte, which is 1 byte subfunction. The other services are parameterized by 2 byte data identifier. This slide shows the 4 services that are reused for OBD and ZEV purposes on UDS. There is the 14, clear diagnostic information, the 19, read DTC information, the 22, read data by identifier, and the 31, routine control. Two of them are parameterized by subfunction byte, the other one parameterized by data identifier. In the last section of my presentation, I would like to show you an example of how to read the VIN with J1979 classic OBD compared to J1979 UDS-based OBD. As we talk about diagnostics on CAN and not on Ethernet, we need CAN identifier. The CAN ID for functionally addressed requests, for example TST to OBD system, is 7DF. As part of the CAN payload, we put the service identifier of the OBD service request. In this example, the request vehicle information service with the service identifier 09. As mentioned before, we also have to tell the control unit what vehicle information we are looking for. As we are looking for the VIN, vehicle identification number, we send the 02 after the 09. So the entire message reads tester to OBD system 7DF, XX, which doesn't count here, 0902 means read VIN. Be aware, as the 17 characters of the VIN do not fit in a single CAN frame, the response must be segmented and finally takes 3 CAN messages. In this part of my example, I would like to show you how to read the VIN with J1979-2. As we still talk about diagnostics on CAN, we still need a CAN identifier. It's the same as we had before. It's the 7DF CAN ID for functionally addressed request tester to OBD system. In this case, we don't take the 09 as the service identifier for the request, but the UDS service identifier 22, which is read data by identifier request. And of course, we also need to specify the identifier, so we need the 2-byte DID of the VIN. In the UDS specification, the 2-byte data identifier of the vehicle identification number is F190. So we would send with the service identifier 22 the F190 as a CAN message with the CAN ID 7DF. But that's not read the VIN with J1979-2, because J1979-2 does not use the DID of ISO 14229 UDS. It specifies its own data identifier of the VIN. And this data identifier is not F190, it is F802. I don't know why, but if you would like to read the VIN with J1979-2, you have to send the 22 F802 to the control unit. With my almost last slide, I would like to summarize my presentation as follows. Scan tool-based diagnostics require a tester, a VCI, and control units. And all components must support the same diagnostic communication protocol, for example SAE J1979-2. In the following, my colleague Julian will focus on the technology of a diagnostic tester.
Thank you so much, Peter, for the great technical introduction and the examples you've presented to us. And a warm welcome to all the participants for today's webinar about OBD on UDS from my side. Here comes the good news. All the technology, what you have heard about so far, is an essential part of what will be presented next and works out of the box. So you don't need to take care about technical details or how to implement future legislation. It's already built in and ready to use. Let me start my presentation with a short real-life story. A few years ago, long before COVID hit, I was presenting a solution to a potential customer. The presentation went well, it was well prepared, all good, until one single question from the potential customer arose, which I was actually not prepared for. They asked me, "Can we change that without your help?" Well, it took me a few seconds to think about, but finally the answer in my head was no. Of course, I tried to overcome that question. I was saying that we can, of course, implement it very quickly. It will be a special price for them, or the resources are available to do it quickly. But this didn't fit their needs. So in the end, we couldn't make the deal, unfortunately. Today, a few years later, I would say we turned about 180 degrees in the other direction. Today, we believe that it's not us, it's you who shall have the total control over every aspect of your individual after-sales solution. We are there to enable customers to design and manage their own solution from A to Z. And this is how we're going to do it. Softing TDX is a toolbox for OEMs and first tiers to design and manage their individual after-sales solution. The technology is based on an off-the-shelf product, but with the highest flexibility in designing the solution. In order to accelerate the process from the first prototype until the go-live solution, we came up with a three-step workflow: design, manage, and work. During the design phase, customers will be provided with so-called content development tools. Here, the actual service tester is being created. You need to take care about the user interface, how the solution shall look like, shall implement repair procedures, diagnostic data shall be created or edited. Additional content like wiring diagrams or any information which is helpful for the service technician in the repair shops can be integrated during the design phase. In the second step, the manage phase, it's all about the integration into existing IT infrastructure. Of course, OEMs and first tiers already have IT infrastructure, for example, content management systems, other usual management systems like Active Directory, or any other database which is available in order to store relevant data for the after-sales solution. The idea of that phase is the integration in the existing IT infrastructure and creating one central point of administration where all the important information which is needed for the after sales is available. And the third step, the work phase, this is where the service technicians use their service application to repair, maintain, and do software updates on the vehicles, and this worldwide. For this presentation, we focus on the tester or scan tool to the EE system. So the next slide will show you an example of how an after-sales tester could look like. So this is an example of how the first impression for the service technician could look like. We've implemented a kind of a dashboard here in order to show the architecture of the vehicle in the central, the ECU network. On the left-hand side, you see important information already indicating with green and red if there are some errors available or not. In addition to that, you see some information about the vehicle, model, year, any other information, the VIN, of course, which is very, very important. Any other information the vehicle is able to show could be presented here as well. So this, what you see here is just a demo implementation. All the data and all what is shown here is flexible to 100%, meaning all what you see is only demo and will be looking completely different to the OEMs or first year's corporate design in the end. This slide shows a detailed view from the ECU level. So we went now a step deeper from the vehicle level to the ECU level. You see on the left-hand side serial number, the software version, any other dates which are important for this ECU. And in the middle, you see 5, we call it diagnostic use cases. Identification, diagnostic trouble codes, data display, ECU refresh, and the configuration. And of course, there are multiple other use cases at the customers, so these could be implemented as well. Next, I would like to show you 2 examples of this diagnostic use cases. Here we see the use case diagnostic trouble codes. So the active DTCs, again, this is in demonstration data. We have 2 active DTCs here with all the freeze frame data, which is necessary. And all that information helps the service technician in the workshops to get to the root cause of a failure. This application, what you see here, is mainly Windows-based, but in the bottom you see these 3 red dots indicating the, I call it swiping mechanism. So all what you see here is not only on Windows available, it's also available on mobile platforms, Android and iOS as well. This is one last example I would like to show to you. We call it the configuration, or you can also call it the parametrization, which is a typical diagnostic use cases. Mainly, this could be used for end-of-line testing or the commissioning of ECUs or vehicles in the end of the production. And again, all what you see here is just a demo implementation. So the TDX workshop or the service tester solution in the end is only a framework. So this framework then is showing your content and it looks fully adjusted to your corporate design. As Peter mentioned during his presentation, it's not only the service tester, but it's also the vehicle communication interface, which is taking care about the communication between the software and the vehicle or the ECU. And for that reason, we found out, and this is due to a long partnership with Kvaser, that their newest VCI, the U100, is a perfect match with our after-sales service tester. So we provide a powerful plug-and-play solution for the service technicians. As you can see, it's a very robust interface. It's a USB to CAN FD interface. It's very handy, easy to use. As I mentioned, it's a plug-and-play solution. It's powered up via USB. It's a reinforced galvanic isolation. It has a really high IP rating, 67 IP rating housing, and it's available with multiple vehicle connectors. So it's not only the D sub connector you see here, it's also the OBD connector, which is used in the vehicles, and many, many more. Let me dig a little bit deeper into the design phase. As I mentioned in the beginning, we would like to accelerate the tester development, and this is how we do it. We do it by assigning different tasks to the respective roles in the company. Meaning for the entire solution in the end, you need different parts. As I mentioned in the beginning, you need the GUI, you need the repair procedures, you need the diagnostic data, but each and every component is being created by a different role in the company. And by providing the content development tools in different tools, we have the possibility to split the work and do the work in parallel with the respective roles or with the respective persons. For instance, at the bottom, the repair procedure specialist is working with another tool than the designer or the vehicle responsible. But in the end, it all comes together, finalizing the solution, the TDX workshop in the end. And here we have some advantages. Of course, as I mentioned during the demo slides you've seen before, that the solution will look 100% to your corporate design. We have different possibilities of accessing a failure. It could be symptom-based, vehicle, or ECU-based, or other methods to get to the root cause. Of course, the GUI will be very modern and up to date. And I mentioned the content, the images, videos, PDFs, wiring diagrams, or any other information or documents which is helpful for the service technicians. But the customers will not only be provided with the content development tools. Part of the solution are the so-called design templates. And maybe you remember this aspect here from the demo slides I showed before, the diagnostic trouble codes. And these diagnostic use cases you've seen before, the diagnostic trouble codes is presented here, are part of the so-called TDX templates. So with these TDX templates, you get a role model where the GUI and the diagnostics is already being prepared and integrated into the solution, and the customers can use them, they can change them, and reuse the knowledge what is integrated here in this TDX templates. And again, this is very important, the split of the graphical user interface and the business logic and the repair procedures again helps us to parallelize the work, meaning the graphical user interface, of course, can be created by the designer, and in parallel the repair procedure specialist takes care about the diagnostic sequences. And this parallelization helps to accelerate the solution. In the end, I would like to give a summary about what we have seen so far. So we've seen the Softing TDX as toolbox for the after-sales solution, including the Kvaser U100 as a bundle with the TDX software. All of it is OBD on UDS ready, so it's based on a future protocol and can be used right away. We talked about design, manage, and work approach, which helps to accelerate the process from the first prototype until the go live of the solution. We've integrated ready-to-use design templates, which again helps to accelerate the design phase because these templates can be reused from the customers for multiple diagnostic use cases. We slightly talked about the backend connection, which is very important, which the Softing TDX solution provides as well. The availability on mobile devices and remote access capability is built in. We haven't touched this in this webinar, but of course, if you would like to know more about, please feel free to contact us at any time. So I would like to say thank you for your attention and handing back over to Tammy.